The granite in the Great Pyramid, if you look at the famous King's Chamber, its walls and its roof are, the ceiling of the King's Chamber are all made with gigantic granite blocks.
The secret of how ancient Egyptians cut granite may finally have been cracked, and it has nothing to do with what Egyptologists have been telling the world for over 100 years. For generations, engineers, machinists, and archaeologists have stood in front of the same physical evidence. Granite surfaces ground flat to within 1/1000th of an inch. Drill cores pulled from ancient sites showing spiral grooves that modern toolmakers cannot explain. Stone joints so perfectly mated that a razor blade finds no gap between them. And the explanation archaeology has offered for all of it, copper tools, sand abrasive, and patience, has never once come close to accounting for any of what those surfaces actually show. Graham Hancock spent 40 years saying that out loud. 40 years of being dismissed, mocked at conferences, professionally buried by the institutions that were supposed to be asking the same questions. Above the King's Chamber inside the Great Pyramid, 5 additional chambers are roofed with granite beams weighing approximately 70 tons each. Shaped, fitted, placed with precision that makes modern structural engineers go quiet when they calculate what would have been required. Then in 2022, a material scientist with no background in Egyptology whatsoever ran the one test nobody had bothered to run in a century of examining these surfaces. He put ancient granite under a scanning electron microscope. What he found embedded inside cutting grooves made 4,000 years ago should not have been there. And it changes the entire conversation. The mystery that was never really solved here is something that rarely gets stated plainly. The pyramids are not actually the deepest engineering mystery of ancient Egypt. Most of those structures are limestone. Engineers understand limestone. They can model how it was quarried, how it was transported, how it was shaped and stacked. The calculations are difficult, but they are tractable. The real mystery, the one that has quietly haunted precision engineers, professional stonemasons, and manufacturing specialists for more than a century, is the granite. Granite sits between 6 and 7 on the MO hardness scale. It is composed of quartz, feldspar, and mica, minerals so resistant to cutting that even today with diamond-tipped power tools, industrial coolant systems, and CNC machinery calibrated to 1/1000th of an inch, working granite is slow, expensive, and punishing. Every professional who works with it knows what it costs in time and tooling. Yet the ancient Egyptians shaped it with a precision that stops modern engineers in their tracks. The King's Chamber inside the Great Pyramid is built entirely from granite blocks, some exceeding 70 tons. The Valley Temple at Giza contains massive granite sections fitted together with joints so tight that no blade can find a path between them. Statues carved from single granite blocks carry surface details so refined that the first engineers to examine them reached for the word machine. And the drill cores recovered from ancient sites display spiral grooves descending into solid stone at feed rates that made a generation of manufacturing professionals set down their calculations and stare. Chris Dunn spent more than 40 years as a manufacturing engineer at facilities producing precision aerospace and industrial components. He worked surrounded by CNC machines, precision ground tooling, and calibrated measurement instruments his entire career. When Dunn examined ancient Egyptian granite artifacts firsthand, his reaction was not academic curiosity. He went quiet. The tolerances he was looking at, surfaces flat to within 1/1000th of an inch across several meters, drill holes maintaining perfect circularity through their full depth, were not merely impressive. They were industrial. He stated plainly that what the ancient Egyptians achieved in granite matched or exceeded the standards of modern manufacturing. Not approximately, not roughly, precisely. At Aswan, unfinished obelisks still lie partially extracted from the living rock where the quarrying stopped thousands of years ago. The largest of them, the so-called unfinished obelisk, would have weighed over 1,000 tons had it been completed. The cutting marks visible in the surrounding granite trench are clean, deliberate, and geometrically consistent across hundreds of linear meters, straight walls, parallel lines, uniform depth. Whatever tools produced those marks were not leaving the ragged, irregular signatures of improvised pounding. They were leaving the signatures of a controlled, repeatable process, one that was understood. The official answer and why it has never worked. So what was Egyptology's explanation for all of this? Copper saws loaded with sand as an abrasive dolerite pounders and time. That was the answer the field had been repeating and defending for over 100 years. And the problem was not that it was controversial. The problem was that it barely worked. And the data had been saying so for decades to anyone who looked carefully. Copper sits at roughly 2.5 to 3 on the MO hardness scale. The quartz component in granite rates at 7. When you attempt to cut a harder material with a softer one, even using an abrasive as an intermediary, the tool destroys itself before the stone meaningfully yields. This is not an archaeological argument. It is basic material science. It was basic material science long before anyone applied it to ancient Egypt. Dennis Starks, an experimental archaeologist at the University of Manchester, spent years designing and conducting controlled laboratory tests of copper tools loaded with sand on granite surfaces. He approached the project as a believer in the conventional model. He wanted to demonstrate that the accepted explanation held up under rigorous experimental conditions. He came out with data that embarrassed it. Progress measured in fractions of a millimeter per hour. Rapid degradation of the copper tools themselves. Surface cuts that were rough, uneven, and bore no resemblance to the polished, geometrically consistent surfaces found at ancient Egyptian sites. Stokes himself acknowledged that the experiments raised more questions than they answered, not different questions. The same questions that had always been there, now with quantitative data confirming that something was wrong with the standard account. Dolerite pounders do work in a narrow sense. Percussion can gradually shape even hard stone. But at the pace those methods operate, shaping even a modest granite surface requires hundreds of labor hours. Scale that effort to the king's chamber with its dozens of massive granite blocks, each requiring finished surfaces, and the labor calculation for granite alone runs into the millions of hours. And percussion still does not explain the precision. You do not achieve surfaces flat to 1/1000th of an inch with rocks and soft metal. For 4 decades, Graham Hancock kept returning to this gap. The physical evidence on the stone did not match the conventional explanation. Something was missing from the story, something significant enough to account for the difference between what the copper and sand theory predicts and what the granite surfaces actually show. And mainstream archaeology responded the same way every time. Hancock lacked formal credentials. His challenges were fringe. Ignore them until he found what was missing. The discovery. This is where the story breaks open. In 2022, Hancock partnered with Dr. Mamdouh Gabr, a materials scientist specializing in tribology, the study of friction, wear, and lubrication at a leading research institution. Gabr had no stake in the ancient Egypt debate whatsoever. He was not an Egyptologist. He was not a historian of any kind. He was a hard scientist, genuinely curious about a hard problem, arriving at it without preconceptions about what the answer was supposed to be. Together, they obtained permission to examine ancient Egyptian granite artifacts using 2 instruments that had not previously been applied to this specific question: scanning electron microscopy and energy dispersive X-ray spectroscopy. These are instruments that reveal surfaces at the molecular level, detail that is entirely invisible to optical microscopes, invisible to every researcher who had examined those same surfaces over the previous century of study. Gabr approached the instrument expecting to find exactly what a 100 red years of Egyptologists said he would find: sand particles, copper residue, the chemical fingerprint of brute force abrasion applied by a softer tool against harder stone. He was methodical. He was skeptical. He had no reason to expect anything other than confirmation of the accepted story. The scan came back. Nothing on it matched the expected signature. The wear patterns were wrong. The scratch profiles did not correspond to sand. And when Gabr isolated and identified what was actually embedded inside those 4,000-year-old cutting grooves, he sat back from the instrument. He looked at the data again. Then he called Hancock into the lab. Random aluminum oxide rating 9 on the MO hardness scale. Harder than anything occurring in Egypt's natural geological deposits in any form suitable for industrial use. Second only to diamond on the entire hardness scale. The same mineral that forms rubies and sapphires in their natural crystalline state. The same mineral that modern manufacturing depends on daily to cut, grind, shape, and finish the hardest engineering materials known to industry. Sitting there embedded deep inside cuts made before Rome existed, before Greece had written its name into history, before most of what we call recorded civilization had produced its first complete sentence. Gabr described the significance in straightforward terms. On the MO scale, you have diamond at the top. The next meaningful step down is aluminum oxide. That gap is precisely why industry depends on it. Cuts what almost nothing else can touch. And there it was in ancient grooves in surfaces that every Egyptologist in the world had examined and assumed contained nothing more unusual than ordinary desert sand. What the corundum actually means. Here is what stopped everyone cold. Corundum does not occur naturally in Egypt in any form or concentration suitable for industrial use. The nearest significant deposits lie in trade regions that ancient Egypt is known to have connected with through long distance exchange networks. Finding corundum embedded in ancient cutting grooves was not just surprising. It meant something with profound implications. Someone had to know what corundum was. Someone had to know where to obtain it. Someone had to know how to process it, how to grind it down, what particle sizes worked for what purposes, how to combine it with a liquid carrier to form an effective abrasive slurry. And someone had to understand precisely why it worked at a level sophisticated enough to sustain that knowledge across the decades and generations required to build the monuments. It was used to build. That is not an accident. That is not improvisation. That is knowledge deep, systematic, deliberately cultivated and transmitted threaded across time. What Gabber said next is the reason this finding cannot be dismissed with a footnote. Using corundum effectively requires understanding mineral hardness at a genuinely sophisticated level. You have to experiment. You have to test systematically. You have to grind the material to specific particle sizes, test results, refine, and test again. The optimization process is not obvious or intuitive. It demands the kind of iterative material investigation that we formally recognize today as the discipline of material science. He was unequivocal. This was not lucky improvisation. This was systematic material knowledge being applied 4,000 years before anyone had coined a name for the field. The secret was not just a mineral. It was everything that mineral implied about the people who used it. The experiments. A single microscope finding is evidence. It is not proof. Hancock understood the distinction clearly, and he understood what had to come next. In early 2023, he organized a series of controlled experimental trials. A workshop, granite blocks, copper tools, 3 abrasives tested head-to-head under fully documented conditions with veteran stonemasons and material scientists working alongside each other. Abrasive 1, sand. The conventional explanation, the answer Egyptology had been repeating for over a century. Abrasive 2, quartz powder, slightly harder than sand and naturally available in ancient Egypt in reasonable quantities. Abrasive 3, a corundum quartz slurry. The hypothesis that the microscope evidence had suggested. The results were not close. Copper loaded with sand delivered approximately 0.5 millimeter of cutting depth per hour. Painfully slow, the copper tools themselves degraded rapidly. The cut surfaces were rough, uneven, and bore no resemblance to the precision found at ancient sites. After a century of repetition as the official explanation, sand produced results that nobody in that workshop would have accepted as adequate. Copper loaded with quartz powder reached approximately 0.8 millimeters per hour, marginally better, still completely inadequate to explain the surfaces and feed rates documented by engineers examining ancient Egyptian granite. Then they loaded the copper with the corundum quartz slurry over 3 millimeters, 6 times faster than sand. The copper tools lasted dramatically longer. The cut surfaces were smooth, clean, and geometrically accurate. And then came the drilling tests. This is the part that silenced the room. The corundum slurry produced core samples with spiral grooves matching the exact pattern found in ancient Egyptian drill cores. The same grooves that had baffled manufacturing engineers for decades. The same grooves that copper and sand experiments had never been able to reproduce under any conditions anyone had tried. Right there in the workshop, cut fresh into modern granite using ancient tool geometries and the recovered abrasive technology. Nick Giza has spent decades as a professional stonemason working granite. He has cut it, shaped it, and finished it commercially his entire career. When the slurry switched to corundum in that workshop, he said the change was immediate and unmistakable. The copper stopped fighting the granite and started guiding the abrasive. The cut went smooth. The speed jumped, the tool wear dropped. He said that for the first time in his entire professional life, watching ancient methods applied to modern stone, he could actually see how the ancients did it. Not theoretically, not as an inference from data, physically in real time with his hands on the tools. But the experiments also revealed something nobody had fully anticipated. The corundum slurry demanded genuine practice skill. Too thin and it lost cutting power. Too thick and it clogged the groove. Pressure had to stay consistent. Feed rate had to be controlled. Every variable mattered and the margin for error was narrow. This was not a process you handed to unskilled labor and walked away from. It demanded craftsmen who had spent careers refining their technique. Knowledge passed from master to apprentice, generation after generation across the entire span of construction. 3 independent lines of evidence: microscopic analysis, experimental replication, and quantitative material science data, all converging on the same conclusion. The secret had been found. But Hancock knew what was coming next because he had been here before. The gatekeeper's Hancock presented his findings at a material science conference in late 2023. Not an archaeology conference, a room full of engineers, physicists, and material scientists. Professionals who evaluate evidence on its merits and carry no territorial investment in the official narrative of ancient Egypt. The response from that audience was largely positive. Dr. James Harold, a geological archaeologist with decades of study in ancient Egyptian quarrying methods, acknowledged something significant. Abrasive slurries do not preserve in the archaeological record. They are used, they do their work, and they disappear. Corundum traces embedded inside ancient cut surfaces may represent the best physical evidence that will ever be recoverable for this class of technology. He called the methodology sound and the finding genuinely significant. Then the findings reached mainstream Egyptology. And here is where the story turns. Some archaeologists engaged honestly and asked exactly the right questions. How much corundum would large-scale granite cutting have required across the full construction timeline? Is there direct archaeological evidence evidence of corundum entering Egyptian trade networks during the relevant dynasties? Could the traces embedded in those ancient grooves represent later contamination rather than original use? These are legitimate scientific questions. Good science asks them, pursues them, and follows the evidence wherever it leads. Hancock welcomed them because they are exactly the questions that produce better understanding if anyone is actually willing to do the work. But a significant portion of the academic establishment did not engage with the science at all. They engaged with the name Graham Hancock, the outsider, the man who wrote Fingerprints of the Gods, the man they had spent 40 years positioning as a pseudoscientist with no credentials and no standing to challenge their field. Their position was explicit and consistent. Hancock's involvement taints any finding regardless of scientific merit. The data did not matter. The experimental replication did not matter. The peer-reviewed material scientists standing alongside him did not matter. The name on the project was disqualifying, and that was the end of it. Hancock addressed this directly in a 2024 interview. He said that Egyptologists had told him plainly that even if he was correct about the corundum, he should not be the one saying it. That his lack of formal archaeological credentials disqualified him from the conversation. Even when he was standing next to credentialed scientists presenting reproducible experimental data in peer-reviewed settings, he put it simply, it was never about the truth. It was about who gets to hold the authority over the story. Consider what that actually means. The grooves were always there. The scanning electron microscope has existed for decades before anyone applied it to these surfaces. The controlled experiments could have been designed and run at any point in the last 50 years by anyone with access to a workshop, copper tools, and 3 grades of abrasive. The secret was not hiding. The institutions that claimed authority over the subject simply never asked the question. And when an outsider asked it for them and came back with an answer, they responded by attacking the messenger rather than examining the message. Evidence does not care about credentials. The corundum hypothesis has continued gaining traction among engineers, material scientists, and a growing number of archaeologists who are willing to examine the data on its merits regardless of who brought it forward. What this actually forces us to accept. The corundum discovery does not validate every claim Graham Hancock has ever made. His broader proposals about lost civilizations and pre-Ice Age advanced cultures remain genuinely contested territory, and those debates will continue on their own terms. That is a separate conversation. But on this specific question, how did ancient Egyptians cut and finish granite with a precision that leaves modern engineers unable to account for it using the tools Egyptology has proposed? The evidence now supports a clear answer, and the conventional explanation can no longer simply dismiss it. What the discovery forces us to accept is this. If ancient Egyptians deliberately used corundum-based abrasive slurries in their granite work, and the microscopic evidence says they did, and the experimental replication confirms it works, then their entire technological profile has to be rewritten. They understood mineral hardness at a level far beyond anything Egyptology had assumed. They maintained long distanciance trade networks specifically to source an industrial material that did not exist in the Nile Valley in usable form. They developed processing techniques for that material, grinding it to optimal particle sizes, mixing it to precise consistencies for different applications, testing and refining across generations that constitute genuine material science practiced thousands of years before the Industrial Revolution formalized the discipline. And they sustained that knowledge across the full span of construction, passing it from skilled hand to skilled hand, master to apprentice, across decades and generations of work. They were not operating on instinct. They were not improvising with whatever stone and metal happened to be available. They were practitioners of a sophisticated craft built on systematic material knowledge. They were not primitive. They were not lucky. They were brilliant, and they have been waiting 4,000 years for someone to point the right instrument at the right surface and finally notice. The closing here is the thing that should unsettle everyone who cares about how knowledge works. The answer was always there. The tribology laboratories existed. The scanning electron microscope existed. The controlled experimental framework capable of testing these ancient manufacturing techniques existed for decades before anyone finally applied it to this question. Nobody ran the test. Nobody looked at 4,000-year-old cutting grooves with instruments capable of revealing what was actually preserved inside them. Nobody bothered to ask whether the stone itself might still contain the microscopic evidence of the tools that created it. Instead, generations of researchers repeated the same assumptions until those assumptions hardened into accepted history. Then Hancock made one phone call, not to another Egyptologist, not to someone invested in defending decades of archaeological consensus. He contacted a material scientist, a specialist who had never spent his career arguing over pyramid construction, had no professional investment in the outcome, and approached the evidence with the one thing science demands above everything else: curiosity guided by measurement. The stone did not know what the textbook said. It simply preserved the evidence. That failure does not belong to Graham Hancock. It belongs to the institutions that claimed ownership over this subject for nearly 2 centuries. They possessed every resource, every laboratory, every microscope, and every analytical tool necessary to investigate these questions thoroughly. Yet, the investigation was never considered necessary because the conclusion had already been written. Settled stories are always more comfortable than difficult questions. Institutions built to preserve accepted narratives rarely become the ones that overturn them. It responds only to physics. The evidence points toward a remarkably sophisticated solution. The ancient Egyptians cut granite using corundum-based abrasive slurries, a technology requiring not only an understanding of hardness and mineral behavior, but also organized supply networks capable of acquiring rare abrasive materials, standardized manufacturing practices, and generations of accumulated practical knowledge refined through experience rather than written theory. This was not an accident. It was an engineering tradition, a tradition developed over centuries by craftsmen who understood their materials with extraordinary precision. They discovered techniques that maximized the properties of natural minerals, refined those techniques through repeated experimentation, and passed them from one generation to the next until they became part of a highly specialized craft. Then somewhere in history, that knowledge disappeared. Not because it never existed, because civilizations change. Trade routes collapse. Skilled workers vanish. Techniques that once seemed ordinary are forgotten, leaving behind only monuments that appear impossible to later generations who no longer possess the methods used to create them. And for more than 100 years, modern scholarship looked directly at those monuments while assuming the answer had already been found. If Hancock was right about this, after spending 4 decades being told he was wrong by nearly every major institution in the field, you are left with a question that becomes impossible to ignore. What else did the official story misunderstand? It responds only to physics. The evidence points toward a remarkably sophisticated solution. The ancient Egyptians cut granite using corundum-based abrasive slurries, a technology requiring not only an understanding of hardness and mineral behavior, but also organized supply networks capable of acquiring rare abrasive materials, standardized manufacturing practices, and generations of accumulated practical knowledge refined through experience rather than written theory. This was not an accident. It was an engineering tradition, a tradition developed over centuries by craftsmen who understood their materials with extraordinary precision. They discovered techniques that maximized the properties of natural minerals, refined those techniques through repeated experimentation, and passed them from one generation to the next until they became part of a highly specialized craft. Then somewhere in history, that knowledge disappeared. Not because it never existed, because civilizations change. Trade routes collapse. Skilled workers vanish. Techniques that once seemed ordinary are forgotten, leaving behind only monuments that appear impossible to later generations who no longer possess the methods used to create them. And for more than 100 years, modern scholarship looked directly at those monuments while assuming the answer had already been found. If Hancock was right about this, after spending 4 decades being told he was wrong by nearly every major institution in the field, you are left with a question that becomes impossible to ignore. What else did the official story misunderstand?